Good morning everyone. Today we are going to present our critical review on metal additive manufacturing, focusing on its core processes, application and current limitations. To ground our study, we selected a 2025 review paper by Zalfa et al., published in Recent Progress in Materials. The primary objective of their paper was to consolidate current knowledge on metal AM modalities, highlight industrial adaptability, and outline future technological trends. However, as critical reviewers, our job isn't just to accept these findings, but to evaluate the strength of their methodology, identify blind spots, and assess the true practical value for mechanical engineers. The reviewed paper categorizes metal AM into 5 main modalities: powder bed fusion, directed energy deposition, binder jetting, sheet lamination, and wire arc additive manufacturing. It showcases how industries like aerospace, automotive, and medical rely on these methods for complex geometries and weight reduction. Looking ahead, the authors emphasize AI and machine learning for defect detection, along with high entropy alloys for extreme environments. While this taxonomy provides a solid baseline, our critical analysis revealed several gaps in how these processes and data were evaluated. Dalia will elaborate on the research methodology and data critique.
On the positive side, the authors aligned the terminology with ISO and ASTM standards, providing clear process distinctions. However, methodologically, the paper lacks a formal systematic review protocol. Without clear inclusion and exclusion criteria, it suffers from selection bias. So, furthermore, the data synthesis is largely qualitative. It oversimplifies complex metallurgical phenomena like residual stress and phase transformations, without providing deep comparative metrics. And most notably, while over 5,500 alloys exist, fewer than 50 are reliable printable today. A key constraint the paper glosses over, along with unverified sustainability claims. Next, Alice will discuss the ethical considerations.
A major oversight in the original paper is the total absence of ethical and regulatory discussions. Metal AM presents unique challenges that engineers must address. First, digital CAD files must intellectual property, piracy, and unauthorized reverse engineering effortless. Second, there is widespread environmental greenwashing. Metal additive manufacturing is often labeled sustainable without life cycle assessment data, accounting for high energy usage and powder synthesis emissions. Finally, the decentralization of metal printing poses a significant dual-use security risk regarding unregulated weapons manufacturing. Next, I'll pass to Braden to conclude on the paper's engineering significance.
Despite this limitation, the paper holds strong significance for mechanical engineering. It shows the shift from traditional CNC subtractive molding to digital fabrication, connecting topology optimization directly with AI-driven parameter control across TRL levels. In conclusion, while the paper lacks systematic review protocols, precise quantitative comparisons, and ethical analysis, it remains a valuable foundation text for understanding current trends. By addressing these critical gaps, future research can more effectively bridge the gap between academic theory and real-world industrial implementation. Thank you for your attention.